So, good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the week 8 problem solving and doubt clearing session for the course State Space Approach to Control System Analysis and Design, which was taught by Professor A.P. Tiwari of IIT Mindi. And this week, we will be considering what is an observer and how there's an importance for time scale separation between the dynamics of the observer as well as the reduced order observer dynamics. And we will also be solving some questions. Okay. So we'll start with week 8. And this week is related to observers. Okay, so by definition, when we consider like you are observing something means you are looking at something, right? So in the perspective of a dynamical system, what is an observer doing is it is monitoring the input and output to a system. So you are monitoring the input and outputs of a system. Okay, as you are monitoring this input and output of a system, what is the objective of your observer is? Observer, it estimates the states of the system. So as we know, we have a system which is given by x dot is equal to ax plus bu, y is equal to cx. This is the usual thing we consider for a linear time invariant LTI system. Okay, so how do we represent it? This is our 1 by s. It shows the integration. So at this side, it is x dot. At this side, it is x, right? And here we have a matrix A, which goes here and comes here. And this is a summary. Over here, we have the matrix B, and this is our input U. And x dot is equal to AX plus BU. And our Y is equal to C. Okay, this is our Y. So this is the general block diagram representation of a linear time invariant dynamical system. And what we will see is like this entire thing. This is my system. And this is my input, and these are my output. So how do you know what is an input? An input is what you are giving as an input to the system, and y is the output is what is your measurements. The outputs are your measurements. Okay. So we had started the discussion regarding state feedback. And we had considered that if we want to do state feedback control, we have a control law which is given by u is equal to minus k into x. Okay, where x is the vector of the state and k is the gain vector. So our u is equal to minus kx. So this requires us to have the knowledge of the states. The knowledge of the states means we need to have the measurements. We need to have the measurements of the states. But suppose we have some state, some temperature, some pressure, or some state which we cannot measure. We are unable to measure. Also, it is not economical always to measure each and every state of our system. Some things are not, we cannot measure, and some things to measure is costly, and those sensors are expensive, and it is not necessary. So what we do in that case is we use an observer. So observer will estimate the states. it will find an estimate of the state which is known as x hat, right? And you will have a good observer if your error, that is your error is the actual state minus your estimated state. If this error is low, this error should be low. Okay, so to minimize this error, there was a observer proposed known as a Leuenberger observer. And its objective is to minimize E of t, the error. Okay, it will minimize the error. Okay, so this is your actual system which is operating, but now you want to find an estimate of the state x. So what you need to do is go to the next page. The observer dynamical system. What is that given by x hat dot, that is equal to a into x hat plus b into u plus some L into the actual output y minus c into x hat. Okay, or your x hat dot is actually what a into x hat plus b into u plus L into y minus y hat. So this, if you will observe carefully, this is your input to the system. This is your output of your system. And this is the output of observer. This is the estimated output of your observer. So what you are doing basically is you are connecting the error between the measured output and estimated output. And by doing so, what you are doing, you will be minimizing the error, the deviation between the states. And so this term, so this is an extra term which is there in your observer. This is an extra term present in your observer dynamics. So in this term, what you are doing is what your observer has, it has your input and your output of your actual system. Now the same input u is fed to your actual, to your observer's dynamical system. And observer dynamics are very similar to your system dynamics. It should be similar. Then only it will give you an estimate of the states. Okay. But you have an extra term which is your correction term. And the objective of the correction term is what? It will try to correct the error between the measured output as well as the output estimated by your observer. And when it takes that correction factor, it will tend to bring your measured output and your estimated output to close to almost zero. And if it is able to do that, then the estimated state from your observer as well as the actual system state will be equal. What is our goal? Our goal is x hat should be equal to x. Okay. This is our objective. This is the objective of the observer. And how is this objective realized? Is when my error, that is x minus x hat, hence becomes equal to 0. Okay, so let's just look into the error dynamics. So we want to look into the error dynamics. What we must do, we must differentiate. This is e dot is x dot minus x hat dot. Okay, this is the dynamics of my error. So what is my x dot? It is ax plus bu. What is my x hat dot? It is ax hat plus again bu plus L into y minus y hat. Okay, so that becomes equal to a into x minus x hat minus L into y minus y hat. Right? So that is A into x minus x hat minus L. This is what Cx and this is minus C into x hat. So that is equal to A into x minus x hat minus LC into x minus x hat. That is why my E dot actually is equal to A into E minus LC into E. So the E dot becomes equal to A minus LC into E. Okay. So this is the dynamics of the error. Okay, these are the error dynamics. So, and based on stability. So now, what if you will observe this error dynamics, it will appear error dynamics appears as an autonomous system. Okay. So if you want this system to be stable, this matrix A minus LC to be stable. Okay, this A minus LC should be stable. And if it has to be stable, what is required then? That means the real part of the eigenvalues of A minus LC, the eigenvalues, real part of A minus lambda LC should be less than 0. Okay, this should be less than 0. Then we can say that our observer is stable. And that means the error will asymptotically converge to 0. And when that happens, my x will become equal to x hat. Okay, also that means your x hat will be equal to x. So your estimate will be equal to your x, right? So that is the power of your observer. And what more? Okay, so the overall dynamics. The overall dynamics can be written as x dot and E dot. This is equal to A B into x into E. This is 0. This is A minus LC. Okay. Plus, sorry. This actually will be A 0 0 into A minus LC into x into E plus B into 0 into U. So this is your overall dynamics. Overall dynamics, which considers your system plus observer. These are your overall dynamics. All right. Now, this dynamics we have found. Now, if this is the A minus LC determines the stability of your observer. So how do we design an observer? Like what is the criteria? Is it just sufficient that your system should be stable, or we need some additional criteria? Okay. So L can be found for observer to be stable, but should there be any additional criteria? So have you guys heard of time scale separation? Like what is that? So time scale separation means the poles of observer should be much faster than the poles of your closed loop system. And why is that? So that your observer will quickly estimate the value of your state. Okay? So that means this is E dot is A minus LC into E. Now, if you will remember in your previous week, in week 7, we had considered x dot is equal to A minus BK into X. Okay, this A minus BK into X. So we had to design K to place the poles, to place the closed loop poles of the system. Similarly, in the observer, we have to design L, okay, to place the poles of observer. So all the previous steps which we have done earlier, okay, all the previous things which we had done, there was various ways. One was the Ackerman, one is the bus Gura algorithm. All of these methods are valid even for our observer design. But there is a slight modification. If you observe, this is A minus BK, here it is A minus LC. So this can be written as E dot is equal to A minus C transpose L transpose E. Okay. Now you can, so you have to use A and C transpose to place L transpose. Okay. This will come when you will be designing it in MATLAB or something. What matrices you must exactly use. If you want to directly use the command, similar command, if you want to use of state feedback, then you have to consider C transpose instead of B. Okay. There is all the modification which is required. So are there any doubts still here? Okay, so let's go to the question. Well, let me see from here. So we have a dynamical system has the transfer function given by g of s is equal to 10 upon s square plus minus 9. Now we have to determine the ABC matrices. We have to find the gain vector to place the closed loop poles at minus 5 plus or minus 5j, as well as we need to design a full order observer. Okay, which where we locate the poles at this. Okay, so we have our system. This is question 1. It's given by g of s equal to 10 upon s square minus 9. 10 upon s square minus 9. So we have to first find the ABC matrices. So how do we do that? So this actually is equal to y of s of u of s. And in this case, we will consider this to be x of s on u of s. Let us show. So 10 upon s square minus 9 is equal to x of s upon u of s. So this is a revision of a concept which you had learned earlier, various canonical forms. How do we find it out? Right? So this actually is s square into x of s minus 9 into x of s is equal to 10 into u of s. So what we do, let x of us s equal to be x1 of s. That is state x1. And s into x of s be the state x2 of s. Okay? And s square of x of s is the derivative of x2 dot of s. Okay? So x2 is equal to s is equal to x1 dot, right? And x2 dot minus 9x1 is equal to 10u. So what do we get? X1 dot is equal to x2 and x2 dot is equal to 9x1 plus 10u. Okay, so now we write this equation. We have our x1 dot, x2 dot is equal to 0190 x1 x2 plus 010 u, and our y is equal to x1, so it is actually equal to 10 x1 x2. Okay, so from this what do we have? We have our A matrix is given by 0910. The B matrix is 010 and the C matrix is 10. Okay, so we have found out the first part of the question. We have found the ABC matrix. Now we have to find the gain vector to place the closed loop poles at -5 plus or minus 5j. Okay. So the second part. The closed loop poles are at -5 plus or minus 5j. So the desired closed loop poles are actually s plus 5 plus 5j into s plus 5 minus 5j. So this can be expanded as s plus 5 the whole square plus 5 square. Okay. So this s square plus 10s plus 25 plus 25. That is equal to s square plus 10s plus 15. Okay, these are the desired closed loop poles. Now, we are using what? We are doing A minus B into K. So our B is what? 0, 10 and K is K1, K2. So BK is 0, 10, K1, K2. That is 0 into 10 times K1, 0 into 10 times K2. So when we do A minus BK, that is equal to what is A? 0190 0190 minus 00 10K1 10K2. So A minus BK is equal to 019 minus 10K1 minus 10K2. So this is the closed loop matrix. So the eigenvalues of this will be given by Si minus A closed loop. So that is equal to S00S minus 019 minus 10K1 minus 10K2. So that is equal to S minus 1 10K1 minus 9 S plus 10K2. So we have to find Si minus A closed loop is equal to 0. So we get S into S plus 10K2 plus 10K1 plus 9 is equal to 0. So we get S square plus 10K2S plus 10K1 plus 9 is equal to 0. So on equating, what do we get? This is our A closed loop polynomial. And our desired polynomial is S square plus 10S plus 50. So what do we get? 10 is equal to 10K2 and 50 is equal to 10K1 plus 9. Therefore, K2 we get to be 1 and 10K1 we get it to be 41. Therefore, K1 should be equal to 4.1. So our gain K is 4.1 and 1. This is our gain vector. These are the values which we get. Gain vector K. Now, if you will look at the question, we have to design a full order observer with the poles located at minus 50 plus or minus 50 J. That means we have to design that L vector, which we will use. Now we are considering the design of observer, which we have x dot should be equal to ax plus bu plus L into this x hat dot is equal to a into x hat plus b into u plus L into y minus c into x hat. Okay, so we have to find this L. So to do this, what are we designing? What are we interested in designing is we have to design this A minus LC. It has to be designed. We are considering this. Okay. Because as I told earlier, E dot is equal to A minus LC into E. So this is the matrix. So our A observer is actually equal to A minus LC. So what is our L? Our L is L1 into L2. Sorry, L actually in this case is given by L1, L2. So what is our C? If you will look back, C is actually equal to 1, 0. So L into C is L1, L2, 1, 0. That is equal to L1, L2, 0, 0. So A minus LC is equal to, what is our A? A is 0190, 0190 minus L1, L2, 0, 0. So that is equal to minus L1, 1, 9 minus L2 into 0. So this is our A observer. So Si minus A observer is equal to S0, 0, S minus of minus L1, 1, 9 minus L2 into 0. So that is equal to S plus L1 minus 1, L2 minus 9 and S. So Si minus A observed, that is equal to S plus L1 into S plus L2 minus 9. That is S square plus L1S plus L2 minus 9. But our desired polynomial for S actually is equal to S plus 50 plus 15J into S plus 50 minus 50J. That is equal to S square plus 100S plus 2500 plus 2500 that is equal to s square plus 100s plus 5000. So on comparing, we get L1 is equal to 100 and L2 minus 9 is equal to 5000, or L2 is equal to 5009. Okay, so this is how you can solve and get it. And if you will see that, notice that this is just a second order system. We had a transfer function. What we did from the transfer function, we found the ABC representation of the system. Once we found the ABC representation of the system, we designed a closed loop, the gains required to get our desired closed loop eigenvalues. Once we got designed those gains, then we also designed our observer system, right? So let us consider it. Okay, what is our A matrix? We'll consider our A matrix is 0190. 0190. And the P matrix is given by 010. 0, 10. The C matrix is given by 1, 0. 1, 0. So these are our ABC matrices. Now, what are the poles of our uh, state feedback? Poles which we got for state feedback are given by -5 plus -5. -5 plus 1 into I into 5, comma, -5 minus 1 into I into 1. So let us see what are the poles. Let's see if I into I. Wait a minute. Here we can see also around this section. So what is our A matrix? So this is our A matrix 0190, B matrix 010, C is given by this. So let us write poles and state feedback equal to, that is what is I. I is given by this. So 5 into I is given by this. -5 plus 5 into I is given by this. -5 minus 5 into I given by this. Okay. So consider this. What is poles? So these are the poles. -5 plus 5i and -5 minus 5i. Okay, so if you observe, they are complex conjugates of each other and the real part is negative, so they are stable poles. Okay. So now if you want to place, we can have this. We can do place A, comma B, comma poles, state feedback. And this is our vector K which we want. Again vector K. So we'll run it. So it comes out to be 5.9 and 1. And if you look at our answer, what did we get? K is 4.1 and 1. We have made a issue. Here comes our mistake. So that this actually is, sorry, you have to cut it. This is minus. Minus. This is minus. So actually it becomes 59 and it comes out to be 5.9. Okay, so this is the error which I made. This actually was a minus sign I forgot to take. That's why we got a wrong answer. Okay, so this is how I'm actually using MATLAB to verify my calculations, and I found my calculation is wrong. I went back and I could find the issue was I misplaced a negative sign. So now this k which I'm getting is matching with the k which I have derived. Okay, so they are matching. So my k will actually be 5.9 and 1. So this is the gain k which is got. Now I'm interested in the design of the observer. And when I'm designing the observer, I will be using C transpose. So in that case, what I will do is I will let us put the what are the poles of my observer that is minus 50 plus 50 into I, comma minus 50 minus 50 plus 50 into I. Okay, minus. Then these are the poles of my observer. Okay, and the L will be actually place of A, comma C transpose, comma the poles of the observer. So when if you look at it, your L will come out to be 100 and 556.556. What did we get L to be? L1 is 100 and L2 we have got it a bit different. Where is the L? A minus LC 0190. L1 to C. What is our C? 10. Check again. So L1, L2. We have L is equal to L1, L2. A minus L into C. Why not? Let me comment this out. So this is A minus LC. This is the observer is A minus LC. Okay. Then since lambda we have determinant of A lambda into E by Q minus A underscore observer. So what is this equation comes out to be? Lambda square plus L1 lambda plus L2 minus 9. This is correct as per our equation. S square plus L1 is plus L2 minus 9 is correct. Now my desired status equation for my observer is given by that is given by lambda minus poles underscore observer, first one of it, into lambda minus poles underscore observer, the second one. Let us see what is the desired characteristic of observer. Comes out to be this. Let us expand. Let's expand expression. Here is immutable n. Will again restart it. It comes out with lambda square plus 100 lambda plus 5000. Which is matching with what we got. Wait for this. So we'll expand. Expand. Finally, with the desired characteristic observed polynomial lambda square plus 100 lambda plus 5000. Where is the order? This will be 8 trans. This was there. So when we will use, we have to use A transpose, C transpose, poles of the option. We cannot use A. We have to use A transpose, C transpose, and the poles. Then we will get as per this. And if you will you notice this 1000 into 0.1 is 100, and 1000 into 5.009 will be 500.9. Okay. So this was the mistake which I had made. Okay, I must use the place of A prime, C prime. So this actually is for observer design. Use transpose of A and transpose of C while using the place command. Okay, otherwise you get the wrong result. So we have checked it live. We have debugged it. We have found it. So let me comment these things. Okay, this is what we have checked for observer design. Okay, let us check for the theory which Sir has taught. Like this is the system x of t, dx of dt. This is your A matrix, C and D. So this is your overall system. And this is your observer. The observer subtracting the output minus your estimated output, which I showed. That is the R, which is minus your residual, that is multiplied by G or L. Okay, I'm using L, but Sir has used the notation G. So we'll proceed further in the further slides for the part of the lecture to consider the notation G. Okay, then you have B into U, and then you have this dz of dt and z of t. And E. Okay, so this is the equation of a full order observer. Here, Sir considers what is known as the residual. So residual is the error of the outputs. Correct? So this Sir has shown. And we can, so for the observer, we need to use A transpose, C transpose. We get a gain, this Z transpose. For the state feedback, we have to use A, B, and we get a gain K. And for the bus Gura algorithm, similarly, we'll have to use Q and W and P and W, the transpose of that, and its inverse, and B0 minus A. Okay, this is the bus Gura algorithm. So your P is your observability matrix, and your W is given by 1, A1, A2, dot dot A n minus 1, 0, 1, A1, A n minus 2, etc. So this is another way of doing it, right? And this is an example similar to the one which we have considered. These are the characteristic polynomial and what is the desired characteristic polynomial if you are close to the matrix A minus GC. And here, so let's consider using Buscar algorithm to find out what is the gain K, gain G, which is the point. Okay. And these are outputs which are as shown. Okay, so let us consider this system. These are our start, and we will design a full order observer having poles over here. So example sum will consider. This is the A matrix. We write A matrix is given by minus 0.2500, minus 0.2500, 0, minus 0.10, minus 0.10, and 0.01, 0.01. So this is the A matrix. The B matrix, we'll write it as 0.11, 0.11, and the C matrix is given as 111, 111. So let us run it and let's just check what is the ABC matrix definition. So this is the A matrix minus 0.500, 0 minus 0.10, and 0.1. Okay, so 0.1.01 is 0.1.01, and B is 0.11, C is 111. So B is 0.11, and our C is 1.11. So they are saying you must design a full order observer having poles at -2, minus 0.5, plus or minus j 0.5. Okay. So what are the pole locations? So poles are at poles of our observer should be at -2, comma minus 0.5 plus minus j 0.5. So it should be at minus 0.5 plus 0.5 into I, and then its complex conjugate minus 0.5 minus 0.5 into I. Okay, so these are the poles of the observer. So let us run. So there is three poles, one at -2, another at minus 5.5 plus 0.5 j, and another at minus 0.5 minus 0.5 j. So these are the three poles. Now we don't need these ABC matrices to be shown. Similarly, this also we have checked it. So now we have to find the gain G. So that can be found by using the command place A transpose. For radio observer based design, A transpose, C transpose, and our pole locations, that is poles underscore observer. Okay. If you will run it, you will get the gain to be 14.02, 5.8352, and minus 17.1976. So these are the poles, like these are the gains which are required for our observer design. So let us, so this is using directly the formula. Let us try using the Buscuro algorithm. So for the Gura algorithm, what we have to do, the steps are shown here. Mm, These are the steps. Okay. First, we must find the P matrix. So let us try with the Gauss-Gura algorithm, which is, let us look at the steps. So P, the matrix P is given by C transpose, comma A transpose, C transpose, comma A transpose, A transpose, C transpose. So if we look at the matrix P, there is some dimension error. Probably it should be like this. Okay, let us run it. Hmm, C transpose. Okay. So the A transpose into C transpose, A transpose into A transpose into C transpose. Okay, it is correct. Everyone. So this is the P matrix which we got. Okay, and if you will remember, this actually is our observability matrix. And if you want to check if our system is observable, we just have to do the rank of P. It is 3, that means it is observable. And there's a direct way in which we can get our P matrix. P direct. It is, we just have to give the observability OBSP and A comma C. And it itself will complete our P matrix. Okay, this actually is a bit different. Okay, this is not this is not the observability matrix. It's similar to it, but not exactly. So now we have this P matrix. Now we have to find our uh, W matrix. Okay. For that, we have to find the eigenvalues of our original open loop matrix. So for that, we will do um, okay, characteristic of my characteristic equation of my open loop system is given by expand or determinant of lambda into EY3 identity matrix of dimension 3 minus A. Okay, let us run this section. This is our open loop characteristic equation. Let me expand it. So um, this is our characteristic equation of the open loop, right? So let us find its coefficients. Find the coefficients of the characteristic equation open loop. So these are the coefficients: -1 by 4,000, 43 by 2,000, 17 by 50, and 1. If we will observe it, let us check this characteristic equation open loop. You will see, okay, where the this loop. So we will define coefficients window. It is given by this. So these are the coefficients of my characteristic open loop polynomial. And if we will have to find, let me just briefly clarify. So we have a matrix which is 3 cross 3. And we do lambda I minus a, we find the characteristic polynomial. That comes out to be lambda cube plus a1 lambda square plus a2 lambda plus a3. Okay. So we want to find this a1, this a2, and this a3. That is what we are interested in finding. So if you'll observe, my a1 is, my a3 is minus 1 by 4000. This is my a2, this is my a1. Okay. So what is my a1? My a1 is, out of this vector, my a1 is the a1 is my third one. This is a1. My a2 is the second one. And my a3 is the first one. So let us check. So a1 is this, a2 is this, and a3 is this. Okay. There is another way to say what is the difference with that? It's leading to errors. Let us do it. Okay, so we got the a1, a2, and a3. Now, what is our W matrix? W matrix is given as 1 a1 a2, 0 1 a1, and 0 0 1 because it is just limited to 3 cross 3. So W matrix is going to 1 a1 a2, 0 1 a1, then 0 0 1. Okay, so this is my W matrix, right? And what is my vector A? This A is A1, A2, dot 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 AN. So A is equal to A1, A2, A3. This is A. So let us check this W and A. So this is my W matrix and this is my A matrix. Okay. So the previous error. Now we have to find what is our desired flow slope. So our desired characteristic equation is given by uh, lambda minus the poles. What are the poles I mean? Lambda minus poles observer, first one, into is entitled lambda minus poles observer, second one, second pole into the third pole. So let us expand this. Run it. This is, it comes in this format. We want to expand it. So we will use the command expand. Okay. So this is the desired characteristic equation which we get. Now we have to find out from this our D. So our D is the coefficients of this desired characteristic equation. Okay. So let us check our D. What our D comes out to be 1, 5 by 2, 3, and 1. Okay, we don't want the last one. So D all is this. And D which we actually want is D all from here. So let me just do simply. So D1 is D all, the second D all the second one. D2 is D all the third one. And this comes in the opposite order. So this is our A3, A2, A1. A3, A2, A1. This comes with lambda 2 plus D1 lambda square plus D2 lambda plus D3. C plus D3. The coefficients of D is given by 1, last one, 5 by 2, second last one, 3. So the last one is my D3. D3 is what? D all 1. D2 is what? D, not D all, coefficients of D. Coefficients of D the first one, coefficients of D the second one, and D1 is the coefficients of D the third one. Okay, so this is my D1, D2, D3, and D is actually equal to D1, D2, D3. Mhm. And this is our D matrix. Okay, let me mark this because we don't want them to show as output. Okay. So now we got B and A. So now what is desired of us is we have to do the steps. G transpose is PW transpose the inverse of that and D0 minus A. So again is PW transpose. So it is actually the inverse of P into W, its transpose into D minus A. Let us check what it comes out to be. Some dimension error. Let us check one by one thing. So first we will do P into W. Okay, P into W is working. Now let us do the transpose of that. PW transpose also has come. Now we do inverse of it. Inverse of PW transpose. That also is coming. Into, let us try into D. I think that is stating the issue because D is defined as, if you will see, D is a row. It's a row vector, but it should be a column vector. So what we must do, we must just define it a transpose. Okay. Define it to a transpose, and then we can do into D minus A. So that is giving us our solution. So it is 4375 by 312. What did we previously get? Okay, 4375 divided by 312. So 4375 divided by 312 is 14.024. Okay, so it is matching. So what G is inverse of this. This is the G which we get. And let us do VPA of this, comma 4. We run it. G actually is 14.02, 5.835, and minus 17.2. And in the previous case, what we got G to be 14.02, 5.835, minus 17.19. Okay, it is somewhat similar. Okay. So this is the logic. So we have used two things now. Let me summarize. directly use MATLAB place command to place the poles, or alternatively used bus Gura algorithm to place the poles. So why is it important for you to know the bus Gura algorithm? Is because in your exam you will not have MATLAB. You need to have a step-by-step way to get the answer. And to do that, you need to know the bus Gura algorithm. Okay, so the bus Gura algorithm is required for you to solve in the exam. Right? So let us actually try the bus Gura algorithm for a simple question. Okay? So we have to design a full auto observer for this system. So let us solve it. We will go for question 4. Our A matrix is given by 0, 1, 1, 1, 0, 1, 1, 1. B matrix is given by 1, 0. C matrix is given by 1 and 3. This is our ABC matrix which we have. So what do we have to find? We have to first find the P matrix. P matrix is what? C transpose, A transpose, C transpose. Okay, because it is only second order. So what is A transpose? We have to do A transpose into C transpose, that is equal to 0, 1, 1, 1 into C transpose means 1, 0. Okay, let us complete this. So 0 into 1 is 0, 1 into 1 is 1. Okay, so this is A transpose, C transpose. So P matrix, which is given by C transpose, A transpose, C transpose, is actually equal to 1, 0, 0, 1. So to our surprise, to our ease, this comes out to be an identity matrix, right? This is an identity matrix. So we got P. Now we have to find W. So to find W, what we have to do? We have to first do the eigenvalues of A, the characteristic equation of A. That is lambda minus 1 minus 1 lambda minus 1. This should be equal to 0. So this is lambda into lambda minus 1 minus of 1 is 0. So lambda square minus lambda minus 1 is equal to 0. Right? So if we compare, so this actually is lambda square plus a1 lambda plus a2 is equal to 0. So we got a1 is equal to minus 1 and a2 is equal to minus 1. Okay. So this is our A1 matrix, this is our A2. Means the A1 and A2 values we got. So our W actually is equal to, you will remember, just check. W is 1 into A1, 0 into 1. So W is 1 into A1, 0 into 1. That is 1 into minus 1, 0 into 1. This is our W matrix. Now what do we have to do? We have to compute P into W. We have to find P into W. Right? So P into W is what? P into W will actually be equal to W because it is an identity matrix. Next, we have to find PW transpose, that is equal to W transpose. So that will be 1, 0, minus 1, 1. Okay, we have gone so far. Now, let us find PW transpose, this inverse of this. Inverse of this. We have to find the inverse of this 2 cross 2 matrix. So what happens? These two get interchanged. So it is become 1, 1. It is the same, so there's no issue. And 0 becomes minus 0, remains the same, and minus 1 becomes 1. Okay, and the determinant of it is 1 minus 0. So the matrix comes out to be 1, 0, 1, 0, 1, 1. So this is our inverse PW transpose. Now we have to find a desired lambda, right? Desired lambda. So desired characteristic equation. So that is what lambda minus 10 plus or minus 15j. So lambda, so it will be lambda plus 10 plus 15j into lambda plus 10 minus 15j. So that is lambda plus 10 the whole square plus 15 the whole square. So that is lambda square plus 20 lambda plus 100 plus 15 square is 225. So that becomes equal to lambda square plus 20 lambda plus 325. We desired lambda. So it has this lambda square plus d1 lambda plus d2. So our d, which is equal to d1, d2, that comes out to be 20 and 325. Okay. So our gain, the gain which we needed, G transpose is inverse of PW transpose into, let me verify, it is D minus A. D minus A. So what is our inverse PW transpose which we got? 1001011. So 1011. What is our D which we got? 20 and 325. 20 and 325 bracket minus, what is our A? A is minus 1 minus 1. So minus 1 minus 1. So if you do that, that comes to be 1011 21 326. So our gain transpose is what? 21 into 1 and 0 into 326, so 0. So 1 into 21 plus 1 into 326, that will be 21 plus 326. So that comes out to be 21 7 347. Okay, so this is our G transpose which we got. So this we have got through bus Gura algorithm. So now let us verify in MATLAB, because I'm a human being. I will make lots of errors and blunders. So let us check. So we are considering second question, where the A matrix is given by 0 1 1 1. So 0 1 1 1, right? The B matrix is given by 1 0. B matrix is given by 1 0, and C matrix also is given by, okay, B matrix is a column vector and C matrix is a row vector. C is, sorry, 1 0. So this is our ABC matrix. Let's just run and check whether it's coming properly. So this is a matrix, B matrix, C matrix. So we have got A, B, C matrix. So now since we have to place the closed loop poles, so we do A transpose, comma C transpose, comma whatever pole location. So the poles of our observer, we want it to be at minus 10 plus or minus 15. So it should be minus 10 plus 15 into I and minus 10 minus 15 into I. This will be poles of observer. Let us run this section. It is running. So we get the gains to be 21 and 347, which we also got over here. Okay, we also got it to be 21 and 347. Okay, so they are matching. So we have successfully found out the gains of 21 and 347. We have computed it and how much time it took us using bus Gura algorithm. It took some time, like maybe 3 minutes or 4 minutes. But through MATLAB, it was very instantaneous, but you cannot use MATLAB in your exam. So this is just for verification. I'm using MATLAB, right? So now let us go on to further topics. Like what can be done? Here is going lecture 25. Okay, this deals with the reduced order observer, which is structure and further aspects regarding it. Okay. So we will consider what is known as the mm, reduced order observer. Now, with some states you can measure, some states you may not be able to measure, right? So why should we estimate all the states? If we are already measuring a state, it may not be required to estimate the state because it will take more computational burden of your hardware resources, etc. So why don't we just restrict our observer or our estimator to just the states which are not available to us, right? That can be done. Okay. So what we will do is we have state x dot is equal to ax plus b. This is our system, and y is equal to c into x. Now what we do is we partition our system. Suppose our y is actually c1, c2, x1, x2. Okay, we partition our state into two halves, into two separate states. Not two separate states, two separate vector of states. This actually is a bit confusing. It should not be x1, x2. Let me make it z1, z2. Okay. So this y c1, c2, z1, z2. Right. Now, so it's raining over here. So now, how do we write our system? We can write it as z1 dot z2 dot is equal to a11, a12, a21, a22 into z1, z2 plus v1, v2 into u. Okay, effectively what we are doing is we are partitioning the system. So we are partitioning the system. Now, what is considered is C2 is 0. C2 is 0. That means my y is actually C1 into x. C1 into Z1. Okay, so y is only dependent on the states Z1. And y is what? Y is actually your output or your measurement. Okay, so y only consists of the states you can measure. Okay, y is a combination of your states which are being measured. Right? So now you can get your Z1, you can easily get it to be P1 inverse of y. This is the meeting will end in 10 minutes, then again you can join the meeting. Right? So y, so Z1 is actually C1 inverse of y. So we have the equation Z1 dot is A11 Z1 plus A12 Z2 plus V1 into U and Z2 dot is equal to A21 Z1 plus A22 Z2 plus B2 into U. Okay, this is the way you can kind of partition the system. But now what they are saying is we have to, since we are being observed, we have to add the estimate of the states. So we have to add the correction factor. It is going to be G1, G2. Okay. Here is add the correction factors that is given by plus G1 into Y minus C into Z1 and G2 into Y minus C into Z1 again. Why? Because what do we do in an observer? In an observer, we are measuring the input of the system we are being observing, its output, and we use the estimated output. So our estimated output in this case y hat is actually equal to c into z1. So that's why in both the equations it is actually y minus c into z1. Okay. So I hope this point is clear. Okay, so y, this is y minus y hat. Now y hat is c into z1, right? So now, okay, and it's actually c into z1 or actually c1 into z1. C1 into Z. So they're saying is we don't want to estimate Z1. We already have, we are already measuring it. So we can have Z1 is equal to X1 is C1 inverse Y. So we need an observer only for the X2 component, only for the X2 component. So this is the dynamic equation for this part. Okay. So, sorry. So Z2 dot is equal to A22 Z2 plus A21 A21 into X1. A21 into C inverse of Y plus G2 into Y minus C into C inverse C1. C1 inverse of Y. Let's just check. C1 into C1 inverse of Y. Let's go. Plus B2 into U. Okay, so this becomes equal to 0. So we get it as Z2 dot is equal to A22 Z2 plus A21 C inverse of Y plus B2 into U. So if you will observe, this is your input, this is also your input. Your observer, both of these are your inputs. So these are the dynamics of your reduced order observer. And if you try to understand, it depends. The stability depends on this A2. Okay, the stability of this depends on A22 and the speed of the system and the speed of your observer, etc., depends on your A22. Now, what is the problem which happens is we are not able to control A22. A22 is defined by your system. Now, you don't have any flexibility to change or to improve the speed, etc. So that's why this mode, this method of the observer is not considered. There's no kind of no sort of design. We are just reducing the equations and we are kind of estimating it. But the performance of this estimator will not be as required. So this design. So what is done in that case is we will consider estimate of x2 using this formula. This is whereby z2 is Ly plus epsilon or some function and that epsilon delta is d into epsilon plus Ey plus Fu. So they have defined another dynamical system. If like kind of another dynamical system is provided and it is being shown to this expression, then we have to actually just solve this. We actually have to just solve this. So what is done is these are the resulting equations which have to be satisfied. So if you look at it, the D is given by A22 minus LC into A21. Okay, this is the D. And what is the thing which we can use for design is L. Okay, we can design L. We can choose L such that we can make our observer's response, our observer's dynamics. Our observer's dynamics depends on this one. This D determines my observer's dynamics. Okay, and how can I design? How can I control? How can I change this B? Is depending on the L which I choose. Okay, it depends on the L which I choose. So this is D which we have. And once we have this D, then we can design our E. Our E is given by E is equal to A21, A21 minus L into C1, L into C1 A11 plus BL plus BL into C1 into C1 into 1. Okay, this is E. Further, F is B2 minus L C1 into B1. Okay, this is the way we can design. So our objective is what we have in our control is this L. This L is our design variable, which we can use for designing our dynamics of our observer. Okay, and this is the E and F matrix which we get. And our effective system. Okay, let me use some easier thing, notation. Let us use our gamma kappa dot is actually equal to d into kappa plus B into y plus f into u. E into y plus f into u. So effectively, what is this? This is my observer. My observer. And what are my inputs to my system? The system is y and u. And then we have our kappa comfort. This one that. And this is multiplied by L, right? What actually this? L into y plus kappa. So this plus L y is our estimated Z2 height. This is our estimated state. So this is the state which we are estimating. This is how we can estimate our state Z2 hat. This can be used to get an estimate of our state, and this can be used as feedback for our state, our state feedback based controller. So now we will go back to our question. This is our A matrix, B matrix, and our C matrix. Let us partition this. So this is our A. This is going by 0, 1, 1, 1. Our B, which is given by 1, 0. And our C, which is given by 1 and 0. So we are partitioning it. So our A11 comes out to be 0, A12 comes out to be 1, A21 comes out to be 1, and A22 comes out to be 1. Our B1 comes out to be 1, our B2 comes out to be 0, C1 is 1, C2 is 0. Right? So what did we see? We have to get this D. Our D is actually equal to A22 minus L C1 into A21. C1 into A21. Okay. We have to design this D in this. Okay. So let the eigenvalue of our observer, the reduced order observer, be at minus 50. We want that eigenvalue to be at minus 50. Right? What is our D? These are A22, that is 1. L is some value. C1 is 1. A21 again is 1. Okay, this is 1 minus L. Okay, our D is actually equal to 1 minus L. Now we know the dynamics of our observer. What is the dynamics of our observer? This is B into gamma plus E into Y plus F into U. So this D determines my eigenvalue. Because it is a unity, it's a dynamical, this observer is a dynamical system of order 1. That means this D value determines my eigenvalue. So this D, I want this D to be equal to minus 15. So I get 1 minus L should be equal to minus 50. So L should be equal to 1 plus 50. So L is 51. Okay, so we designed our L, we got it to be 51. Now what should be my E? The E will be given by A21 minus LC1 A11 plus BLC1 C1. That is A21 minus LC1 A11 plus BLC1 C1 LC1 C1. That is equal to 1 minus. Oh, just hold on 1 minute and this. Sorry, actually there's a time stop. So E the A21 minus L is 51 into C1 is 1 into A11 is 0. This is 0. Is B is actually what? Minus 50 into L is 51 into C1 is 1 into inverse of 1 is 1. This is 1 minus, so 1 plus 50 into 51. This becomes equal to 1 plus 0, 5, 2, 5, 2, 5, 5, 0. So it becomes equal to 2, 5, 5, 1. What is F? F is given by F is equal to P2 minus L C1 B1. B2 minus L C1 B1. So our B2 is what? 0 minus L is 51 into C1 is 1 into B1 is 1. So our F is equal to minus 51. So our reduced order dynamic equation should be equal to gamma dot is equal to d into gamma plus u into y plus f into u. Gamma dot is equal to minus 50 gamma, sorry, kappa plus e is 2551y minus 51 into u. So this should be the observer which we are using in our closed loop, in our implementation. So that, and the x2 is equal to L into y plus gamma. Okay, so our x2, that is a x2 hat which is being estimated, it is 51 y plus gamma. Okay, so this is how this reduced order observer has to be implemented. Right. Next, let's just go through further details which sir has shown. So these are the equations, and this is how the estimates are written. And this is the overall block diagram. So this is our system. So we have B into U and A into X is equal to X dot. That gets integrated, we get our X. And C comes out to be Y of T. And this is C1 inverse. So C1 inverse is our Z bar. Now, the same U is again an input to our observer, to the reduced order observer. So it comes, U is comes. Again, Y is coming. We have FU plus EY and B into this, whatever this epsilon variable. This is our epsilon dot. We integrated, we get epsilon. And our estimated observed value of the state, Z2, is given by L into Y plus epsilon of T. This is our reduced order observer implementation. Right? This is how it is implemented. Okay. So sir has considered one sum, which is given over here. And he has found out the desired characteristic polynomial and found out N, F and all. And he has also done certain simulations for it. Okay. So this is known as a Leuenberger reduced order observer. Okay. And it is a feedback system. It takes both the input and output of the system as inputs and its own state as feedback. Okay, it is taking its own state as feedback. So it is a feedback system. It has input and output of the system. And it estimates all the state variables of the system for which it is designed. It is designed for these many particular states. It estimates those states. Okay. Now, can I use these estimated state variables for my closed loop implementation for state feedback based control? So that is shown in the next lecture. So what was taught till now was we are designing. We want to design controllers, thinking that we have the states are known to us. But what if the state is not known? Then what we are doing, we are designing an observer. But can we use these observed states, which may not be equal to our actual states, to design our controller? Can it be used for actual implementation? Because it is not always possible in any system to measure all the states. Okay, some states are not accessible, some states are difficult or hazardous, and it is not practical to actually measure all the states. So in that case, what these control system engineers have found out is that we can use an observer to estimate what is the value of the states, and then we can feed back this those measured states as well as the estimated states to as a control input, and we can control our system. And this is only valid if we follow what is known as the separation principle. Okay. So, what is the separation principle state? Is that we can design our controller, our state feedback controller, using the previous known method, in which we assume that we have all the states, and also we can design our observers separately. Okay, they are decoupled. Like what has happened is we are decoupling the design of our controller and we are decoupling the design of the observer. But if we want to have a good response, there are certain thumb rules which have to be used. But it is a very good, very challenging, a breakthrough concept, which is shown that we can decouple the controller design as well as we can decouple the observer design. Okay, so we can do that separately. So that is the what is known as, and that has been proved using time scale separation. Okay, so the poles of the overall system can occur using full state feedback, and we can also design the observer poles as well. Okay, so there I can see feedback system design using full order observer. Okay, u to minus kx, we can design our controller. Now this is our observer. Z dot is into az plus bb plus z into y minus cz. So another point, limitation in this Leuenberger observer is we need to exactly know our system dynamics. That is, we need to know our A, our B, and our Y, and our C, etc. This may not always be in practical life, they will vary, they will change. Those things have not been considered in these analysis. Okay? So these things will further require simulations and there will be further advanced concepts to get into, right? So what is done is we have an observed value of the state. And instead of actually feeding back our x minus kx, we are feeding back minus k into z. We are feeding back the estimated state. Right? So it has been shown that there is a decoupling. If you will observe this matrix, x dot e dot is equal to a minus bk, bk, 0, a minus bc. So this matrix, if you look at it, it is a upper triangular matrix. So the eigenvalues of this upper triangular matrix depend only on the diagonal element. So we can decouple, we can design our state feedback here, and we can design our observer dynamics. Right? So this has been shown. And also feedback system design using reduced observer also has been shown. Where this is the way they are using a reduced order observer to determine our closed loop control system. Okay. And, so again, we have decoupled the closed loop state feedback system and the eigenvalues of the reduced order observer. They are again decoupled. This has again been proved again. So these are the, if I'm using full order observer or if I'm using reduced order observer, I can design my controller, my state feedback controller, using the previously known method, assuming I have all the information of the states. Then in my actual implementation, I have to design additionally an observer, a reduced order observer, which will give me the estimate of the states I don't have access to measuring. And using these estimated states plus the measured states, I can actually implement state feedback. So this is what happens. Okay. And here, sir, I solved one sum. And in the example, so all these when we do, we assume that our system is observable, the system is controllable. So if our system is observable, then only we can find the estimates of the state. If it is not observable, we cannot estimate it. Right. And if our system is not controllable, we cannot do state feedback and get design and force the poles to our design location. It would not be possible. So first thing, whenever you are working on your project and your practical system, you have to check your system is controllable. Then you can design some gain scale to control the system. Then, if you find that you are not actually able to measure all the states of your system, you cannot implement state feedback. Then you will have to use the observer. Then you have to check whether your system is observable. And once you check whether your system is observable, then you can design an observer. Okay? So these things Sir has shown. Sir has also used the LQR concept to design the gain scale, right? And also the poles Sir has also shown. And Sir has shown certain simulation results to show the effectiveness of his implementation. All right. So actually, currently in this session we couldn't show much of simulation results. Any simulation result was not possible to show, but we will try to see whether it is possible in the next further sessions. All right. So let me do a brief recap of of today's session. So today's session was all about observers. What an observer does. It takes the input of a system, it takes the output of the system, and from that it will estimate what is my actual state. What are the internal states of a system? That is the job of an observer. Okay. And there are various criterias, various things which are to be fulfilled by the observer. All right. So why observers are very important is when we want to implement state feedback control, right? And we do not have all the states for us, then we can use an observer which will estimate our states. Okay. And what we want to do is the Leuenberger observer, which was proposed, which has been shown in this session, its objective is to minimize the error. Its goal is to just to minimize the error. So we have an observer dynamical system, and in the observer dynamical system is it has the same dynamics as my original plant, plus there's an additional term in which we are correcting the observed output as well as the output of our estimated output. Okay, we are actually correcting that. So this property, that is, we have our output and we are correcting with our observed estimated output, and this correction is what enables the estimated state to actually converge to our actual system state. Okay. So we are actually correcting the error between the measured output and estimated output. And in this process, we are actually making or forcing our estimated state to be equal to our actual state. So the objective is to minimize this error. And this error dynamics depend on this A minus LC. So we have to choose our L in such a way that this matrix A minus LC is stable. For it to be stable, we know the criteria for the LTI system is the eigenvalue should lie on the left half of the S plane. That is, they all should have real part negative. Okay, suppose we do that also, still it may not be sufficient. Our system might still be slow, our observer might still be slow. So if our observer is slow, that is, it takes a long time for us to get the estimate of a state. It would not work as we want. The system response would not be good. So in practice, the dynamics of our observer is much faster than the dynamics of our actual system. And what do we mean by the dynamics of our observer? We mean the error, the deviation of the estimated state from the actual state, that dynamics, that correction of that dynamics or that error will be much faster as compared to our system, which is being observed, that dynamics. Okay. So this we have shown. And as I mentioned, poles must be much faster. Poles must be much faster. That means it must be more to the poles must lie more further away from the real axis, from the imaginary axis. All right. So we can design the poles, the gains K using Ackermann or Bus-Gura algorithm. I have also shown the MATLAB demonstration of that. And Bus-Gura algorithm is useful if you are actually doing using pen and paper. Okay. gives you a fast method. So the power of Baskerville algorithm will be understood when you are doing for a third order system or fourth or a higher order system. Right? In the exam, I think it will be only limited to third order, but Baskerville algorithm is a better way for you to do. Second order system can be designed a little bit easier as compared to third order. The complexity is smaller. Okay. So this is our transfer function. And what we had to do was we had to find the ABC matrices. We had converted into canonical form and we found our A matrix, B matrix, C matrix. Right? After we found these matrices, we found what is our desired closed loop pole location. So we got a desired characteristic equation. Then we found out what is our actual closed loop equations in terms of K1, K2. And then we equate them and we found the value of K2 and K1. K1. So there was some error, mathematical error, which was found out while verifying it using MATLAB. Then we checked designing of the observer and how do we set. Again, we found the desired closed loop characteristic equation of our observer and then we compare. Okay. Next in question 2, what we did was we had to design a full order observer and then we further added stuff regarding to a reduced order observer we did later. Right? So what we did, these are the ABC matrices we have. We found the P matrix. Then we found A transpose, C transpose. We got our P matrix, which turns out very luckily, it turns out to be an identity matrix. We found out its eigenvalues or the characteristic polynomial of it, and we got our A1, A2, which is needed. Then the W matrix was found, and then PW transpose turns out W transpose and its inverse which we found. And then we got what is our desired closed characteristic polynomial. From that we get D1 and D2. Once we get that, we found our gain vector formula. Okay. So then we consider reduced order observer, which we consider, and in this case, the C2 has to be equal to 0. Then only all these things are valid. If it is not equal to 0, then there should be a certain modification which has to be done. Suitable modification will be required to be done. Okay. So this also was done. What are the equations? What are the inputs to our reduced order observer? And how the observer dynamics have to be written. This is the dynamical system of my observer, of the reduced order observer, and how they are used to estimate the state Z2 and. Okay, and then we did this partitioning for the ABC matrix, which we had considered for problem 2. And then we designed D. All right, we found what D is required, what L is required. And once we got that, we found our E matrix and F matrix, which was needed. And then we found out the dynamical equation of our observer and what is the equation for estimating the state X2. Okay. So this is the summary of what was done in today's session. And in next week's session, it will be related to more about sampling, multi-rate sampling, further aspects regarding digital control. All right. So thank you for joining this session, and I will end it now. Thank you.